from today. So that's Wednesday. What would that be? I can't remember. Yeah.
Okay.
Wednesday next week, the last Wednesday before spring break.
That was the second. I'm not 100% sure.
Okay. I'll post it on D2L. Okay. No. March 2nd. Okay. And the topics are everything up through rigid body kinetics. So, in the assignments coming up, I'll make sure to include some stuff that'll, won't be new stuff. It'll just help you get ready for the test. And today we're just going to keep going with rigid body kinetics. Anybody have any questions about? I forgot to. So last time, I made a mistake in the last equation of the, what was the problem? The pulley with where we included the mass. I posted the correction, like if you go to the course notes, the correction is just the last couple lines of the lecture, and it's done in red, so you can see what the mistake was. It was just a sign error. From last time, there was a sign error in the last equation. It's corrected in red in the class notes. And if you fix it, what you get is, so the system was like this. What were the masses of these? Okay, so 10 kilograms and 20 kilograms. Because of the mass difference, the 10 kilogram box is going to accelerate up. If you have a massless pulley, the acceleration of the 10 was 0, positive 3.27 meters per second squared. If you have a mass, and what did I have the mass as? 1 kilogram? Is that right? And a radius of 0.05. The acceleration of the 10 kilogram was equal to like 3.22 meters per second squared. And so what's happening is now instead of the cable being able to produce any acceleration it wants with no resistance to this pulley when it's massless, now there's some inertia in the pulley. And so some of the force exerted by these cables is used to overcoming that inertia of the pulley. And that's why you would expect that acceleration to be smaller with mass, and that's what you get. Okay? All right. So the next thing I want to do is a rolling without slipping problem using kinetics. We've talked about it with kinematics, but we didn't have any way to predict what kind of accelerations we would get. Kinetics. I think I said kinematics. And so we're still going to use the definitions of rolling without slipping. So rolling without slipping means give me one of them. So the closest one to that is that the velocity at the bottom point is equal to 0. So there's no, at that point that's in contact, instantaneously there's no change, there's no difference in velocity between the ground and the point. What's another one? That's right. So that's just another way of saying that the acceleration of the center is parallel to the surface. It's not bouncing up into the air. So the perpendicular part of the acceleration of the center is equal to 0. And then there's one more.
The acceleration at contact parallel is 0?
Yep, exactly. So the acceleration at that contact point, the component that's parallel to the surface, is equal to 0. So there still can be centripetal acceleration of that point, but there's no acceleration due to the tangential part of acceleration. It's not exactly centripetal and tangential because it's that relative motion problem, but it's the part of the acceleration that's parallel that's equal to 0. So it doesn't slide. Okay, so now what we're going to do is we're going to think of a solid disk rolling down an incline. I'm going to give you some parameters for it. And we're going to calculate the acceleration that comes from it rolling down this incline. There's an easier, faster way to do this problem, and that's using energy methods. Basically, anything you can do with force methods, you can do with energy methods, and vice versa. Some problems are just easier to do one way or the other. This one's easier to do with energy, but we're going to do it this way because it's a good example of it reminds you about rolling without slipping, and it's a good example of how to do rigid body problems. So let's say that we have an incline of 20 degrees. And a solid disk. Oh, that's a terrible circle. Let me try again. Oh, that's worse. Okay, I'm only going to try one more time. I don't trust those. It loses the soul when you do that. You know what I mean? Like, where's the passion? Okay, so this is the center. Let's say that the radius is 0.1 meters. Okay, everyone with your hands, show me what 0.1 meters, a circle with 0.1 meter radius looks like. Show me the size.
It's 10 centimeters. That's like that much.
Yeah, right. So 10 centimeters. 10 centimeters, I don't know how much that is either, but that's the radius. So the circle's like this or something. Okay? Yeah, somewhere around there. Okay, and the mass is, let's make the mass 1 kilogram. And we want to calculate the acceleration of the center. And to do this, to simplify the calculations, there's no reason you have to do this, but a lot of the stuff we're going to see is parallel to this direction or this direction. So let's make the coordinate axes like that. Okay, well, what we're trying to do is we know something about a force. Really, we know something about a couple force directions. We know the magnitude and direction of the weight force, and we're trying to translate that into an acceleration. So thinking about it that way says Newton's second law and the rotational equation. The other thing is you're like, yeah, we're doing rigid body kinetics, and everything goes through those same 7 steps. So let's try those. Either one of those two thought processes works here. All right, so if we're trying to head towards Newton's laws, what's the first step in doing these kinetics problems? No looking.
Diagram.
That's the third step. That's a key step. That's the question. Yeah, the first question. I got too excited. I need to save my voice. I have another class today. I should have come in with one of those little microphones that like super old professors use. So the first question is, does this have a fixed point or not? It doesn't. Even though the velocity is 0 at that bottom point, a fixed point is one that can't, where that point on the body doesn't have velocity and it doesn't have any acceleration. So this isn't really fixed, even though instantaneously it has 0 velocity. So there's no fixed point. And what do we use that information to tell us? Yeah, that's right. The about point is the center of mass. And now what's step 2? That's right. Good job with the math. Yeah. So mass moment of inertia about the center of mass, which is what we're calling C. This is a disk. Is it rotating like a blade or a paddle? Blade. Any rolling is rotating like a blade. So this is mr squared over 2, which is 0.01, 1 times 0.01 over 2, so 0.005 kilogram meter squared. Third step is the free body diagram. Okay, so what force? Yep. Yes. Thank you. So what are some forces acting on this? Okay, that's true. Let me go in. I shouldn't have even asked because I wanted it in a specific order. Okay, yeah. So the first one is weight. That's how I always want you to think about it. Just like weight, contact, weight, contact. I want you to be like, take all the creativity and fun out of it. Just first, the weight. That's so it has a mass of 1 kilogram times 9.81, so 9.81 newtons down. And now the contact force, and we have to think about that a little bit. What's the nature of the contact force? There is a normal force. That is correct. What about friction?
It's in the direction opposing motion.
That's right. And how do we know there's friction? Well, that's right. If there was no friction, it would just slide down. And we're going to see that you can see that's not happening because if you did this well, it's sort of a circular logic, I guess, but if you had a block sliding down an ice incline or whatever, and then something rolling down the same incline next to it, the thing sliding without friction would accelerate more than the thing rolling. That friction force reduces the acceleration that we're going to get. And so anyways, yeah, if rolling without slipping requires a friction force, that's what keeps it from slipping. So that's going this way.
Does it matter which way you draw it? If you get it wrong, will it be negative?
In this case, it matters if you're approaching the boundaries of the strength of the static friction. So this is static friction, right? Because that point doesn't have any velocity. If you were trying to figure out the boundary between slipping and not slipping, then your choice would be important, I think. And definitely if you were dealing with sliding friction, your choice of direction is important. But I think in this case it would come out either way. Just do it the right way. Okay. It never hurts to draw it the way that it's actually going to go. Okay, so now step 4, pancake table. This step isn't necessary, it just helps you organize your thoughts. Pancake, artists, row 4, marzipan. I am going to choose the origin to be at the temporary center of this rolling disk. So it's important to understand for later on when we have to make distinctions between inertial and non-inertial coordinate systems, that I'm not saying the coordinate system's origin is at the center and moving with it. I'm saying that that coordinate system is hovering there in space, and at the instant that we're analyzing, that wheel's center rolls through the center. Okay. So the location of the center is at the origin. We'll make, well, no, we don't have a choice about where to make the about point. The about point has to be at the center, so that's the origin. Subtract, you get a row vector of 0. And now, what about that force vector? Well, we're breaking it up into a y component and an x component. You can do that trigonometry without too much trouble. You can also, by the way, use a rotation matrix to do this. The people who are taking D-form right now, we've done a ton of stuff with rotation matrices. In dynamics, it's funny because in dynamics, the class, rotation matrices don't really come up, and I don't tend to talk about them, but when you're actually doing dynamics, you use rotation matrices a ton because you're often trying to relate coordinates you're getting in this crazy coordinate system to coordinates in this coordinate system. Well, they would be facing the same way. But and so you have to use rotation matrices all the time to relate the components here to the components here. The way this would work is your rotation matrix. So in a standard coordinate system, we know what the weight force is. It's 0, negative 9.81. So just use a rotation matrix that transforms vector components from that standard coordinate system to our rotated coordinate system. What would that, for the people in D-form, what would that rotation matrix be? What would the angle be? Well, it's a 20-degree angle, so that's like way off. Negative 20, yeah. So yeah, exactly. I'm too predictable. Not in this case. No, because you don't do that. You go from the original one to the rotated one. Times 0, negative 9.81, and you get sine of negative 20 times 9.81. Negative, and negative 9.81 times cosine of negative 20. And what do you get numerically for that? Could someone punch that in?
I got 3.355 and negative 9.218.
Okay. And you can sanity check with the signs of those, and that makes sense. Okay, so that's just for the people who are working with rotation matrices. Remember, rotation matrices, you know, they transform vectors from one coordinate system to another. That's all we're trying to do here. So this is a time that it works if you have it easy access to it in your calculator. You never have to think about trigonometry again on these kind of problems. So the force vector is 3.355, negative 9.218. Cross product is 0. And now we'll go to that contact point. What are the coordinates of that contact point? That's the origin.
0 radius, just right.
That's right, and negative. Because, this is going to be 0, negative 0.1. The about point is zeros. Row vector is 0, negative 0.1. I'll start with that normal force. So what are the components of the normal force? Yeah. 0 positive n. And the cross product there is 0. And then the friction force is at the same location. So the row vector is the same. And what are the components of the friction force? Negative F0, yeah. Negative F sub F0. And the cross product is negative 0.1 force of friction. Okay, so what's step 5 in these kind of problems? Newton's second law. You don't always have to use it. Do we have to use it here? Yes, and why? That's right. So if you have a fixed point, you usually don't have to use it. I would say always skip it the first time around. If you need it later, go back to it. This one doesn't have a fixed point, so Newton's second law because no fixed point. So Newton's second law will take all of these and add them up. So 3.355, negative 9.218, plus 0 n plus negative FF0 is equal to the moment of inertia times the angular acceleration. No. This is Newton's second law. So it's equal to the mass. What was the mass? 1 kilogram? Times the acceleration of the center, which I'm going to write as AC0. And by the way, this is using, this is using one of the assumptions about rolling without slipping. We're using the fact that in rolling without slipping, the acceleration is parallel to the surface. So in rolling without slipping, the acceleration of the center is parallel to the surface. That's what let me simplify that acceleration vector. All right, so what's the sixth step? Yep. So Rn2L. That just says we only have one moment, so negative 0.1 FF is equal to the moment of inertia times the angular acceleration. The moment of inertia was 0.005, and the angular acceleration is alpha. What we got so far? Okay, so we have some equations, and we have some variables. Let's count them all out, write them all out, and see what we got. So our equations, the first one says negative FF minus AC is equal to negative 3.355. The second equation says N is equal to 9.218. The third equation says negative 0.1 FF minus 0.005 alpha is equal to 0. And what do we have for variables? FF, AC, N, and alpha. So we have three equations, four variables. We're just trying to calculate AC, and so if you look at these equations, N just appears by itself. So let's not simplify. I hate simplifying. Let's just keep it like this. The more equations, the better. Okay, so we need one more equation to relate, at least an equation that relates two of our variables without introducing any new variables. Where's that going to come from? That's going to come from, yes, that's going to come from considerations about, so in general it comes from the watermelon equation and relative motion. In this case it's going to come from considerations of rolling without slipping. So yeah, we're going to relate the center to the angular acceleration by the rules of rolling without slipping.
Could you also relate friction and the normal force?
No, because this is static friction. So remember with static friction, yeah, with static friction, all you can calculate is the maximum. If it's not sticking, if it's not slipping, we know we're not at the maximum, and so. All right, so now we'll go to rolling without slipping, and this is that step 7 that you often need. So of those rules of rolling without slipping, these 3 rules, what's the one that's going to help us here? Well, we've already used, velocity isn't really going to help us. We're not talking about acceleration. We're dealing with it. We're not talking about velocities. We're talking about accelerations. So 2 and 3 are kind of the possibilities. We've already used 2. So number 3 here is the one that's going to be useful to us. So the acceleration of B relative to the ground is equal to the acceleration of B relative to the center plus the acceleration of the center relative to the ground. And we're going to use this only for the parallel part because we know that the acceleration of the center relative to the ground only has a parallel part. And so the acceleration of B relative to C, parallel part, is equal to alpha cross R plus this, but this part is perpendicular to the surface. That's the centripetal acceleration. So we're going to ignore this. We're only dealing with the parallel parts. So we have 0, 0, alpha crossed with, what's our R vector from this? So we're talking about, now we're imagining that the center is fixed, and we're calculating the motion of that bottom point relative to the center. So relative to the center, what's the R vector? Yeah, 0, negative 0.1, 0. And so you get positive 0.1 alpha 0, 0. The acceleration of B relative to the ground, parallel, is equal to 0. And so now we can write an expression for the acceleration of the center relative to the ground, parallel, which is equal to 0, 0, 0 minus 0.1 alpha 0, 0. This one we've already given an expression for. This is AC 0, 0. And so now you have the relationship that AC is equal to negative 0.1 alpha, or equation 4, AC plus 0.1 alpha is equal to 0. Any questions about that step? So really, the tricky part about that step is the same. It's the kinematic rolling without slipping. It's the stuff that you've already done before. And so now we have 4 equations for 4 unknowns. Just putting this here so I can see them all. And let's write out an augmented matrix for this to solve it. So here's equation 1, 2, 3, 4. And for variables, let's go AC negative force of friction, and alpha. Doesn't matter what order you do it in. Okay, so equation 1, this should not say negative. Okay, so FFs, we have negative 1 of those. ACs, we have negative 1 of those. Alphas, 0, and 0, and the constant is negative 3.355. Equation 2, n's, we have 1, no other variables, and the constant is 9.218. Equation 3, FFs, we have negative 0.1. Alphas, we have negative 0.005. No other variables, and the constant is 0. And then equation 4, we have ACs, 1. Alphas, 0.1. And no constant. So yeah, can a couple people do this? And as soon as 2 people have ones that match, we'll call it a day.
I got the answers.
Okay.
I got acceleration of the center is equal to 2.23, 67.
Okay.
Force of friction is equal to 1.12, and alpha is equal to negative 22.37.
Oh, alpha. What's the normal? Or did you just left that one out?
I didn't calculate
Okay.
normal.
What's alpha?
Alpha is negative 22.37.
Okay, good. Okay. Oh yeah, we already knew that one. Okay, so there's the acceleration of the center for this disk, rolling right down the incline. And I think on the homework for today, I'll give you a problem where you have to do this for like a hollow disk or a disk with a piece missing out of it, or a sphere. What you'll see is that all of these things with different moments of inertia are going to have different accelerations. So let's just quick do this for, like, imagine a block or a disk, but not rolling, just sliding down a frictionless incline. So what do you expect the acceleration to be? More or less? More. Yep. So 20 degrees. Let's say this block has a mass of 1 kilogram. So what's the acceleration down the incline? Okay, I think I'll just do it. So a free body diagram of the block. We'll use this rotated coordinate system again. So there's a weight of 9.81, and now only a normal force, N, and that's all the forces. So Newton's second law says, well, it's the same weight force, so what was that, 3.355, negative 9.218. So 3.355, negative 9.218. The normal force is 0 n. And the acceleration is going to be all in the x direction. And so equation 1 here says that AC is equal to 3.355. So you can see the difference in the accelerations. Okay, cool. So let's stop there. We have 10 minutes. Anybody have any questions about homework problems or anything like that? Yeah.
For Monday's problem, the one that was in number 4,
Okay.
was the disk rotating around the pin,
Uh-huh.
and we were relating strength point acceleration of point A.
Yeah.
How would you approach it? Like, for example,
Anybody have it with them?
I do. It's going to be mostly, my question is about part B.
Okay.
Because part A was
Okay. Yeah, so let me just draw out the whole problem. So you have a disk rotating about a pin that's not at the center. So usually whenever you're dealing with a disk, you're doing rotations about the center. But this one, the about point is here, and you're calculating accelerations of this point A. The radius is 0.5 meters. The mass is 20 kilograms. And there's an external couple. Oh, there's weight and an external couple. Of negative 100 Newton meters act. And at this instant, this already has an angular velocity of negative 2.5 radians per second. So part A says, what's the angular acceleration? And part B says, what's the acceleration vector of the point A? So I would go through the steps on this. Is there a fixed point? Yeah. So the about point is equal to that point P. The moment of inertia about P is 1/2 mr squared, plus you have to use the parallel axis theorem. You almost always have to do that if there's a fixed point, unless the fixed point is at the thing's center of mass. Third, a free body diagram. Looks like this. You have the weight acting down. You have a pin there. Call that R. And then you also have an external couple. It's negative, so it's clockwise of 100 Newton meters.
Is it, I don't know, the coordinate system's weird.
Oh, is it? Okay. Yes. So let's draw it in the given coordinate system. So I guess someone like me would do a weird coordinate system like this so that you would have to think a little bit about the directions of those couples. So external couple of negative 100 Newton meters. Well, x is still, oh, x is into the page. Okay, this is a pain in the ass. I know. Okay, well, so that means that this couple is going that way if it's negative. All right. And the angular velocity, okay, we'll deal with that later, but that's negative, which means it's also going to be going counterclockwise. So then Newton's second law and the rotational equation, that'll let you solve for the angular acceleration. And the signs are going to look funny because we have this funny coordinate system, and the components are going to look unusual because we're not in the xy plane. And then you're going to go to step 7, and so this is a little hard to wrap your mind around, but it's rotating about this point P, and we're looking at, we're trying to calculate the acceleration of this point A. And so the circular motion that you care about is this, you know what I mean? And so your r vector is this. And so that makes it all this is a little bit odd, but it's all the same steps that you're following. And then you use, you don't have to use relative motion because there's a fixed point. But the acceleration of A is, yeah.
Question, so to find the alpha,
Mm-hmm.
just use the moment, like, moment is equals to inertia times the alpha, like negative 100 is equals to whatever we get for the...
That's what you're going to use for the rotational equation, but there are two moments. There's the moment produced by the weight, and then there's the applied couple.
Okay.
So be sure you get everything in there. Don't just see the negative 100 and then think negative 100 is going to be equal to I alpha. Any other questions about that one? Yep. Find what? Where's D? Oh, this distance? Yeah, you're going to have to use a little trigonometry. But just remember that anytime you have a problem like this, when you're calculating, you're using the watermelon equation to calculate an acceleration of a point around a center or around a fixed point or whatever. The r that you want is from the center of that circular motion. So from the center of the object, if that's your about point, or from the fixed point to the point that you care about. So if you don't think about this enough, you do it too quick, it's pretty easy to make the mistake of thinking that the r vector we want is from the center of this circle to A. But in this case, what we're calculating is the circular motion of A about that point P. Any other questions? Okay.